Hello everyone, thanks for coming to the presentation. I am Juan Camilo Sanguino and I'm going to present a part of the research of my magister degree work with my advisor Ruben Manrique, my professors from Universidad de los Andes, Olga Mariño, Nicolás Cardoso and Mario Linares, and in agreement with GCF Global Foundation. The research called Log Mining for Course Recommendation in Limited Information Scenarios. I'm going to start with a little introduction about the context, motivation, and the challenge. Then the architecture proposed, the data processing, the evaluation methodology for the models and the results, and finally with the conclusions and the future work. In the context, we have GCF Global, that is the foundation where the research was carried out. GCF Global has worked for more than 10 years with the aims to teach the basic and necessary skills for the 21st century. They has an online platform with courses like, for example, how create an email, and in the platform the users can access without a register and without cost. GCF have more than 360 courses divided in more than 6,400 lessons with more than 2,500 videos and 50 activities. The content is enabled in three languages: Spanish, Portuguese, and English. About the users, in 2021, GCF registered more than 40 million devices connected in the three languages. This is a high number of users on the platform. In the motivation, the majority percent of the traffic on their platform are new users. These users may have difficulty finding interesting content due to their lack of expertise in the areas they are interested in. For this reason, GCF want to increase the rotation rate of their users and improve the learning experience. With this idea, a recommendation system could be the solution because it helps the user to find relevant content and keep the interest of the user on the site. In the challenge, the main challenge to implement the recommendation system is the low information scenario. In this scenario, the information is limited because the users don't need to register. As a consequence, the system doesn't have information about the users. We only use the information that comes from the interaction on the platform. The platform tracks the behavior of the user by the device, so we work with the suppose that we have a user by device and a user use always the same device. On the other hand, the platform cannot track the content lesson viewed by a user. So we work with a second suppose that when a user accesses a lesson, he completes it. So with this scenario, how to build a recommendation system? For this challenge, we propose the next architecture that we divide in four components. The first one is the data processing, where we use two data sources: Google Analytics that contains the user logs, and the MongoDB that contains the course information. The second one is the model generation. The idea is to create two models, collaborative filtering and a content-based, that works the independent way. This is very important because GCF start a process to increase the user data that they can get. So it helps us to change the models with the new information without changing the general architecture. The next one is the hybrid system. We build a hybrid model that merges the results of the previous models. And finally, the generation of the recommendation list. In the paper and the presentation, we focus on the collaborating filtering model that uses similarities between users to provide recommendations. In the data processing, for the research, we use the Google Analytics source, where we only take the users of English language in the 2021 year, that is more than 20 millions of users. We filter the user with more than 30 sessions, and then we take a sample of 11,000 users to the data processing and to train and test the model. We load the logs of these users, we order the information by the timestamp to improve the performance in the operations. We calculate the lesson time per user, we get the total number of lessons by course, and we calculate some necessary values for the experiment, like the total of lesson by course per user, the percentage of lesson per user course. We use the term user course to identify the combination of a particular user with a particular course. And the other value is the average percent of the lesson by course per users. For this model, we work only with users who have between 3 and 49 courses to delete the outliers. The total of users after the filter was 7,072, and with this user we split the data in two sets, 30% to test and 70% to train. The previous filter guarantees that in the case the user have 3 courses, we can train the model with 2 courses and test with the other one. In the evaluation methodology, to evaluate the model, we use precision at k. The literature suggests use 5 or 10 value to k, but given the variety of the courses per user, we use a custom k that depends on the courses in the test set by user with a limit of 5 courses. That is the maximum of courses in the recommendation list. To validate the statistical significance of the results, we use the Wilcoxon test. To apply this test, we create 100 samples with 3,000 users in each group, and we calculate the average precision at k. To evaluate each hypothesis, we use a p-value of 0.05 with the von Ferroni correction. The first step to creating the colorating filtering model was to estimate a rating by each user course. To estimate the rating, we use a scale between 0 and 5, and we create a penalty threshold that defines if a user course gets the maximum rating or is penalized. We test with two thresholds, PU, which is a custom threshold created with the average percent course by user, and the GPC, which uses a global average percent. To penalty the rating, we use 5 functions, quadratic, linear, logarithmic, square, and step function. In the graph, we have an example of the process where the threshold is the yellow line. In this case, is the 0.8% of the lesson by course, and all of the values under this threshold giving a penalty using the 5 functions. When we test the model using the total database, we can see that the quadratic and square root functions have the highest precision, and to validate the results, we carry out different statistical significance tests. First, we want to validate which threshold strategy is better using the evaluation methodology and Wilcoxon test. We identified that the PU threshold has better results independent of the penalty function that we used, and the p-value obtained also validate that in the majority of the cases the best threshold is PU except when a quadratic function is used. With the best threshold, we test the best penalty function and we identify an interesting behavior, where a higher penalty has a negative effect in terms of precision. The order of the function from best to worst was square root, logarithmic, linear, quadratic, and finally the step function. We can see the p-value test where the majority of the comparison with the square function are below the p-value with the von Ferroni correction, except for the comparison with the quadratic function. Now we have the best penalty function and the best threshold, but what about the lesson duration? Does it have an impact in terms of precision? To evaluate it, we filter the data using intersession and intra-session duration. The graphic shows on the x-axis the filter by the lesson duration, and on the y-axis the precision and the number of users. We can see that the precision increased as the duration increased, but the total of users in the model decreased as the filter increased. In the end, we have zero point 0.1 more than precision, but the dataset was reduced by around 75%. In conclusion, we can generate a model with a precision at K of 0.39. We can implement a system to estimate the rating successfully, where the best threshold is the custom threshold by user and the best penalty function is square root. Also, we detect that the lesson duration have an impact in the precision, but as a consequence, can reduce the data size. In the future work, we have two important points. The first one is to implement the content-based and hybrid model of the architecture proposed. And the second one is to do a A/B testing in the platform to measure the impact of the recommendation system on the rotation rate. Before finish, obviously, thanks to GCF Global for the funding and dedication throughout the research. And thanks everyone for your time.